In the next series of problems, I'm going to talk about an idea known as a decomposition of a rational expression by partial fractions. Okay, the problems you're going to be working with are going to give you some kind of a rational expression. An example might be something like 7x plus 17 over x squared plus 4x minus 5. And they're going to ask you to decompose it into partial fractions. Okay, well, what exactly does that mean? So that's what I'm going to be talking about in the next couple of videos. We're going to look at a couple of different approaches that'll work. And this comes back to a lot of the strategies that we've already seen from working with rational expressions. So for starters, let's take a look at this. So the concept is that you're going to try to break the fraction into a sum or difference of terms, at least for starters, that all have denominators that are linear. Okay, if you notice right now, my denominator is a quadratic term. Okay, now I still think that's not very clear, so let me talk a little bit about what's going on here. You're always going to start out by trying to factor your denominator if it can be factored. Okay, this denominator can be factored. Okay, if I factor this denominator, it's going to be the quantity x plus 5 times the quantity x minus 1. Okay, so x plus 5 times the quantity x minus 1. Okay, and here's the concept. Okay, normally, because you need common denominators when you add fractions, you can't just take a fraction. Like if I had, if I had 5x plus 1 over x squared plus 4x, okay? I can't take that and just say, oh, that's 5x over x squared plus 1 over 4x, okay? Doesn't follow common denominator rules, okay? If you found common denominators here and you added these together, you would not get this, okay? If you pick a random value of x to put in here and you substitute it into this expression, it's not going to work out to be the same thing as this other expression. Okay, so the idea here in general, you can't break up a sum or a difference of a denominator and break something up into two different fractions. You can break up a sum or difference in a numerator. So for example, if I had something like 5x plus 1 over 7x to the third, I can break this down as 5x over 7x to the third plus 1 over 7x to the third, because when you add fractions, if you have common denominators, your denominator would stay 7x cubed, you would add your numerators. So we've had this idea, probably going back to Algebra 1 for most of you, that you can take a numerator and break it up as a sum or a difference as long as you keep that common denominator, okay? So that is a way that you can break a fraction up, but it's not what we're going to be doing here, all right? Here's what we're going to be doing. So if you look at this factorization, I've got the quantity x plus 5 times the quantity x minus 1. What we're going to do here is we're going to break this up into two separate fractions using each of these as the denominators. So I'm going to break it up into something over x plus 5 plus something over x minus 1. Okay? And again, I can't just split it up, okay? I can't just do 7x over x plus 5 and 17 over x minus 1, okay? If you try to do common denominators and things like that, you would not end up getting an equivalent, okay? But anyway, it turns out that it should just be a constant value over basically a linear term and another constant value over another linear term. All right, so how is this going to work? Well, there are a couple of ways you can do this, and I'm going to show you kind of the most straightforward way of doing it, and I'm going to show you some progressively faster ways of doing it. First of all, you really need a common denominator to be able to add two fractions, okay? So if you take a look at our original fraction here, your common denominator can be found by multiplying x plus 5 and x minus 1, okay? So technically, you can just find a common denominator. This denominator would need an x minus 1, and I would also need to multiply the top by x minus 1. Okay, to get a common denominator over here, I would need a term of x plus 5. So I would multiply this denominator by x plus 5, and because it's a fraction, I would also multiply the numerator by x plus 5. Okay, so the left-hand side doesn't need to change. I've got 7x plus 17 over the quantity x plus 5 times quantity x minus 1. There's no reason to multiply that back out. Over here, I can simplify. I get ax minus a, if I multiply through here, all over that common denominator, plus bx plus 5b, all over that common denominator. Okay? Now, I have common denominators, which means I can add the two fractions on this side. And when you add fractions with common denominators, you just add the numerators. The denominators are going to stay the same. All right? So I've got 7x plus 17 over the quantity x plus 5 times quantity x minus 1. And over here, it's going to be equal to the sum of those numerators. And I'm going to group some things together here just to save a little bit of writing. I'm going to add all of these together. I'm going to put the two x's together, so ax plus bx. And I'm going to put the two values that don't have x's together, so minus a plus 5b, and then all over that same denominator. All right? So now if you take a look at this, notice that you have a fraction equal to another fraction, but they both have the same denominator. And if they both have the same denominator, it doesn't matter what value of x I put into that denominator, as long as it's legal, and it's not going to give me a denominator of 0. It doesn't matter what value I put into that denominator, these denominators will be the same. So I don't really care about the denominators. I care that 7x plus 17 works out to be equal to ax plus bx minus a plus 5b. All right? Now you look at that and, on the surface you think, oh my gosh, I've got x's, I've got a's, I've got b's. This is going to be a 3-variable system. It's going to be really complicated. And it doesn't really have to be that bad. Okay? Here's the key to everything. And the first time you look at this, you may not see it. But I did group things in a way that maybe would help. If you notice here, there's an x term and there's a constant term. Okay, if you notice over here, we have some x terms and we have some constant terms. Okay, these two things have to add together to give me 7x. These two constant terms have to add together to give me 17. Okay, so you can even tighten this up a little bit. For example, I could factor out an x here. I could write this as x times a plus b, and then we've got minus a plus 5b, and it's supposed to be equal to 7x plus 17. The point here is, I've got a 7 paired with the x here, I've got an a plus b paired with the x there. That tells me a plus b has to equal 7. Okay? Meanwhile, 17 needs to work out to give me the constant value over here. So negative a plus 5b needs to give me 17. And so yes, we will get a little system. This one's really nice. If you add these two, the a's cancel, you get 6b is equal to 24. That tells me b is going to be equal to 4, okay? So in my original equation up here, and I know I've kind of marked it up, but my original equation, b is 4, all right? And 4 plus 3 would give me 7, so I would have a 3 for that a value, okay? So the partial fraction decomposition here would end up looking like this. Basically, I'm allowed to take this expression, and if I need to, I can rewrite it as 3 over x plus 5 plus 4 over x minus 1, and that's what's called the partial fraction decomposition of that original rational expression. All right. Again, if you're looking at that and you're saying, why would I ever need to do this? The primary use for this is something having to do with integration and calculus. So not real useful in a pre-cal course, but it will be useful down the road. Okay. By the way, there is a faster way to do this. It ties into something we talked about when we were solving rational equations. You don't have to do it this way, but just to remind everybody. So we had an a over x plus 5, and we had a b over x minus 1. If you remember, the second approach to doing rational expressions or solving rational equations was to multiply the numerator by the common denominator, and that would cancel out all of your denominators. And it will make this a little bit faster. You don't have to do it this way, but it will make things a little bit faster. So if you notice here, the common denominator is going to be x plus 5 times x minus 1. So you can multiply the numerator here by x plus 5 times x minus 1, okay? And you can multiply this by x plus 5 times x minus 1. And you can multiply this by x plus 5 times x minus 1. Okay, so I can multiply the entire numerator by the common denominator. And take a look at what happens. The common denominator cancels. I'm just left with 7x plus 17. Here, the x plus 5 denominator cancels. I'm left with a times x minus 1. Here, the x minus 1 denominator cancels. I'm left with b times x plus 5, okay? And you end up with 7x plus 17 is equal to, you'll get an ax, you'll have a bx, so there your x terms are, and then you'll have a minus a, and you'll have a plus 5b, and you can see, oh, a plus b needs to give me 7, and oh, negative a plus 5b needs to give me 17, okay? And then you can solve that, and of course you find out that b is 4 and c is 3, just like we did before. So a little bit faster. It does give you an equation that's a little bit less messy because it just knocks out that denominator. So whether or not you just want to find common denominators and just do it like you're in an Algebra 1 class, you can do it that way. Or if you prefer to multiply the entire thing by the common denominator, just knock out your denominators, that also works great.